Okay, in this lesson I want to continue our work on finding particular solutions to differential equations. So again, we're given this question, we're asked to solve dy dx equals 2y, so that means solve for y, given that y is equal to 1 when x is equal to 0. So I'm going to try to solve this equation, try to find the value for y in terms of x. And given some conditions on my variables here, y has to be 1 when x is equal to 0. So I start by just finding the general solution to the differential equation. So given dy dx is equal to 2y, can I separate? Well, I'm going to do two things to separate. I'm going to multiply on both sides by dx, getting my dx over on the right. And I'm also going to divide on both sides by this y, so I'll get a 1 over y here on the left. It'll cancel the y on the right. And so my new differential equation is this. I've got my y with the y differential over here and my x differential over here. The next thing is to integrate. I've separated. Now I'm going to integrate. I'm going to take the antiderivative of 1 over y and take the antiderivative. Notice I've factored out 2 from the integrand over here. So I've factored out a 2. So now it's just a case of integrating. And, you know, formula and tables booklets, this is standard integral. You should probably know it. That's telling me that the natural log of the absolute value of y is equal to 2. And again, there's a hidden 1 in there, which we generally don't bother writing in. I'll put it in this case. So the antiderivative of 1 with respect to x is x plus the constant of integration. Okay? And that's kind of a general solution. I'm going to leave that alone for the moment, and I'm just going to address my initial conditions here. It says, but y is equal to 1 when x is equal to 0. Okay, therefore, substituting in, so we know that the natural log of y has to be equal to 2x plus c, so substituting in 1 for y, we're going to get the natural log of the absolute value of 1, which is, of course, just 1, is equal to 2 times 0 plus c. So we have the natural log of 1 is equal to c. Now, what is the natural log of 1? Well, the natural log of 1 is the exponent to which e is raised in order to get 1, and that exponent is 0. So the constant of integration here is 0, which tells me that the natural log of the absolute value of y has to equal to 2x. Okay, has to equal to 2x. Really, I want to solve for y here. So I'm going to solve for y. Well, 2x is the exponent to which e is raised in order to get y, or the absolute value of y. So 2x is the exponent to which e is raised in order to get the absolute value of y, which means that y could be equal to plus or minus e to the power of 2x. Okay, so I've got two solutions here, two particular solutions, but I have to check them both. So we've got y is equal to e to the power of 2x, or y is equal to negative e to the power of 2x. Now remember my initial conditions, that y has to equal to 1 when x is equal to 0. So if I plug in 0 into this first equation, we get y is equal to e to the power of 0, which is 1, so that's fine. But if I plug 0 into this second equation, we get y equals negative e to the power of 0, which would be negative 1, which is not fine. That is no good. That is not my solution. Therefore, my particular solution in this case is y equals e to the power of 2x. That is my particular solution, and that's how I'm solving. So y is equal to e to the power of 2x in this case. Note, I got two values for y. Y could be e to the power of 2x, or y could be equal to negative e to the power of 2x. But both of those answers, both of those solutions didn't work for the conditions given on the variable. So if I get two answers, I've got to check them both. And that'll often happen because of this absolute value sign. Okay, so particular solution in this case, y is equal to e to the power of 2x. Let me look at one more example. It says solve dy dx equals xy given y equals 3 when x is equal to 0. Solve dy dx equals xy given that y is equal to 3 when x is equal to 0. So again, step 1 is to find the general solution, and then I'm going to use the point to find the particular solution. I can use the general solution to find the particular solution at the point 0, 3. X is 0 and y is 3. So step 1 is to just separate here. We've got dy dx equals xy, and there's a couple of different things. Actually, I'm doing the same two things as I did in the last one. I'm going to divide on both sides by y, and I'm going to multiply on both sides by dx. Multiplying by dx on both sides will cancel this dx in the denominator over here. So I get a dy, and I get my dx over here. Dividing on both sides by y will cancel this y, which will just leave me with that. I'll rewrite that to come out very clearly. That's an x dx. Dividing by y is giving me 1 over y. Okay, so we've separated. We have the y terms on the left with the y differential and the x terms on the right with the x differential. And now I'm going to take the antiderivative on both sides. Just like before, the antiderivative of 1 over y is the natural log of the absolute value of y. And that's equal to, well, the antiderivative of x with respect to x is x squared over 2, but plus c, the constant of integration. Next thing, I'm going to address my conditions on my variable at this point, right? So I'm going to just address the conditions on my variable now. So we're told that y has to equal to 3 when x is equal to 0. So I'm going to substitute in, or in fact, let me just write in. So we're told that, so I'm just going to write down nice and explicitly here, but we know that y has to equal to 3 when x is 0. So therefore, well, the natural log of the absolute value of y, well, the absolute value of 3 is just 3. That's equal to 0 squared over 2 and plus c. Okay, which tells me that c, the constant c, is just the natural log of 3. Now you can approximate that, but there's not any point. It's not a very nice looking number. I would just tend to leave it as the natural log of 3. So therefore, let's go back to my general solution here. The natural log of the absolute value of y is equal to x squared over 2 plus, well, the constant of integration, which is the natural log of 3. Okay, let me just tidy that up. Some poor handwriting there. It's been a problem. Okay, so we've got, this is what we have here at this stage. Now, one thing I could do here is I could group my logs together. So maybe I might say the natural log of y, subtract the natural log of 3, is equal to x squared over 2. And if I know my laws of logs, which again we went through before, you've got to know your laws of logs, I can express this now as a single log. This is the natural log of the absolute value of y all over 3, and that's equal to x squared over 2. Okay, so we're piecing bits together a bit at a time. So now I can say, and again, what does that mean? Well, the natural log of the absolute value of y over 3 is the exponent to which e is raised in order to get the natural log of y over 3. So what we're saying here is that x squared over 2 is the exponent to which e is raised in order to get the absolute value of y over 3. I'm going to triple both sides, so the absolute value of y is equal to 3 times e to the power of x squared over 2. So I'm going to have two solutions here again, and I'm going to check them both. You know, you might generally find that both of them are not viable solutions. So what does this mean? Well, this means that y could equal to 3 times e to the power of x squared over 2, or y is equal to 3 times e, sorry, negative 3 times e to the power of x squared over 2. I'm just going to check my solutions again. Again, looking at the initial conditions. The initial conditions here, we were told that y has to be 3 when x is 0. So y is 3 when x is 0. And you can see, you know, plug in 0 in here. You get e to the power of 0 over 2. That's e to the power of 0, which is 1. 1 times 3 is 3. But if I plug in 0 over here, I'll get y equals negative 3. That is not what we want. Y has to be positive 3 when x is 0. So therefore, I just have left to make my final statement. Therefore, y has to equal to 3 times e to the power of x squared over 2. And that's my final kind of answer. Okay. Okay, so remember, you know, you find the general solution first, and then you can use that general solution to find the particular solution that satisfied the point, given what we call the conditions on the variable, often called the initial conditions. The conditions on the variable. So if I know the initial conditions and I know the differential equation, I can find a particular solution in that case. So practice, practice, practice.